Today we want to talk about functions of two variables, and we're going to talk about functions of two variables by starting off talking about functions of one variable. So we already know a lot about functions of one variable, but I want to make sure that we have the right framing around it. So I just want to set a baseline for what we all agree on. So when we have a function of one variable, so a function of one variable, represents a one-dimensional curve in two-dimensional space. I suppose I could be pedantic and be like the graph of one function of one variable is a one-dimensional curve in two-dimensional space. But we're going to think of a function of one variable as a one-dimensional curve in two-dimensional space. The two-dimensional space part comes from the fact that I have two variables running around, x and y. But we're restricting ourselves by requiring that one of the variables be a function of the other variable. So this two-dimensional space part, which we are going to refer to as R2, is because we have x and y. All we're doing is picking a bunch of points, x, y, in the plane. And if we graph a continuous function, they're all going to be connected. And the connection is going to be a one-dimensional curve. By requiring that y be a function of x, that means each input x will correspond to, at most, one output y. So that's the one-dimensional curve part. Each input x corresponds to, at most, one y. Each value of x corresponds to, at most, one value of y. Could be none value of y, but at most one value of y. Note that each y could correspond to multiple values of x. But as far as the way writing y as a function of x, as long as each x corresponds to only one y, or at most one y, we'll get a function. We're going to imagine this, creating the curve, by imagining the value of the function as the height above the corresponding x value. So we build a graph. So we'll say f of x is the height of the curve above the x-axis. So we're going to look at the value of the function. We're going to keep that as the height above the x-axis. At each location x, we just mark a height above the x-axis. If it's negative, then it'll be the height below the x-axis. For each of these x values, we have some height above . These are all things that we already knew. We knew this. We knew that the graph of function makes some kind of curve. We knew that the curve can't overlap. Each x corresponds to at most one y. And we know that we think of the function as the height above the x-axis. Whatever words we used to think of that before, we're just creating a common language right now. We're imagining the value of the function being the height over that x. We're imagining the graph of a function of one variable to be a one-dimensional curve in two-dimensional space. Now we're going to upgrade this. We're going to keep the function part. We're going to keep framing this in terms of a function. But we're going to go up to a function of two variables. So now we're going to have two inputs rather than one input. We're going to make a function of two variables. The input would not just be x from the x-axis, but we're going to take as inputs an x and a y from the xy plane. So we need a third variable. We're going to call it, very cleverly, z. We're still keeping this function format. Z is going to be a function of x and y. We're keeping the restriction that z can be written as a function of x and y. So whatever this is going to represent, it's going to represent it in three-dimensional space because I've got x, y, and z. Whatever it's going to represent, it's going to be in three-dimensional space because I've got an x, a y, and a z. And we're going to refer to three-dimensional space as R3. Because we have three things running around. We have three variables, but the function is of two of them. So to make this R, you just write an R and then put an extra vertical on. If you were typing this on a typewriter, not like a computer, like a typewriter, then what you would do is type a capital R, then you would backspace it, but you would like not backspace it all the way, and you put another R a little bit off. And that's why you get how you get the double R. It's not quite bold, although sometimes when we're typing on computers, we just make a bold face capital R. And the 3 and the 2 indicating the number of dimensions, that's going to be written as an exponent, not as an exponent, it's going to be written as a superscript. And we're just going to say R3 or R2. So now each point xy corresponds to at most one z. That's still a requirement from the function part. So because I said function, so the same thing is going to happen down here. Because of this function business, each xy corresponds to at most one z. Geometrically, we're going to do the same thing with the height. We're going to say the value of the function will be the height above all the points x, y. So f of xy We still haven't decided what it is, but it's going to be the height of whatever geometric thing we get. Not the x-axis. It's not going to be the height above the x-axis because we've got a whole plane to work with. Each xy, we're going to have a height above it. So it's going to be above the xy plane. Now we just got to figure out what that's going to look like. We typically lay the XY plane flat with the x-axis coming out the paper and the y-axis going where the x-axis normally is. So this is how we normally draw the R3. We have x and y are two perpendicular axes, and then we just put a third one perpendicular to these two. And that's our z-axis. So here's how we typically draw R3. Just like we typically draw the positive x-axis going to the right, and the positive y-axis going up. So now the positive x-axis coming out, the positive y-axis going to the right, and the positive z-axis is going up. This was an arbitrary choice that we made a long time ago. We, like I was there. Now, rather than draw some funky curvy thing like we did for functions, I'm going to pick something super simple. I'm going to say, what if we had the function at every point f of xy, we just get the value 2. Simplest thing possible, just like we did when we were learning math in the first place. Start with numbers. Just start with constants. What are we going to get if above every point on the xy plane, I plot the height 2? I've got a height of 2 above every point on the xy plane. What are we going to get? We're going to get a plane. Any more description of the plane? It's going to, the height everywhere is going to be z equals 2, so it's going to be parallel to the xy plane. It's just going to, we're going to take the xy plane and translate it up 2 units. So it's going to be parallel to the xy plane. It's just going to be nice and flat. So at the point 2, we're going to end up with this plane. Above every point on the xy plane, we plot a height, at most one height. Now, this was the simplest version of this. I just used the constant function. But this would just be like graphing the function y equal f of x equals 2. We just get a flat line. Now, if I start adding some variable into it, it starts tilting, like f of x equals 2x. I'll get a line with a slope of 2. If I start with a f of x equals x squared, then I'll get a parabola, and things will start to bend. So I need a more general description for what's going on here. So what we're going to do, what we're going to say is that a function of 2 variables represents a 2-dimensional surface in R3. Eventually we'll run out of words for these things. We're in a two-dimensional surface. But we can see how things go with functions. If I increase to a function of 3 variables, what space are we going to have to be in to make a function of 3 variables? How many variables are running around? I got 3 as inputs and 1 as output. So a function of 3 variables is going to be some object in R4. How many dimensions will the object be? 3. So a function of 3 variables will represent a 3-dimensional solid in 4-dimensional space. Everybody picturing 4-dimensional space? No, right? It's like no. Our perception is wired to this 3-dimensional space. We'll have to look at 4-dimensional space in slices. The simulation would be to use like time as a 4th dimension, but it's not the 4th dimension. We might have 4 space dimensions. It might be meters, 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 and meters. We're just going to have to pick one of those meters and look at it through time. Because we're going to have to look at it in slices. But that's what happens when we have a function of a bunch of variables. Any questions? So a function of 2 variables represents a 2-dimensional surface in 3-dimensional space. How's that, okay? See, I told you Calc 3 was the easy one. This is in the editing. I would stop the video and like start chopping this up into smaller videos, but I don't do video editing. So I just put up raw footage the whole time. I wonder if like during an hour of math class, I probably put out maybe 10 minutes of actual content, especially if I put it up to like 1.2 speed, where it sounds like I'm talking fast, but it doesn't sound like I'm talking comically fast. You know what I'm talking about? What I'm thinking is I need to do is chop this up into like just a bunch of TikToks and not have like 40-minute videos on YouTube, because no one wants to watch a 40-minute math video on YouTube. But if I'm like, oh, it's going to be a minute long, and I go, all right, I can sit for a minute. And then I just have to find the most effective words and images to combine to make you absorb some piece of this idea in a minute. I'm not sure I like where the direction that goes, because the most effective short videos are the ones that piss you off. The most effective thing to spur you into action and to keep you going and watching is to make you angry and disgusted. You know what I mean? Like we like to sell people on like hope and like happiness and stuff like that. That doesn't sell as much as like fear and anger. I'm gonna say humans are a pain in the butt. I think what we're most mad at is that the algorithms have noticed. The algorithms notice like, oh, you know what these humans like? They like being angry and they like being afraid. And the rest of the algorithms like, oh, that doesn't seem right. It seems that like it sounds like they think they want to be happy. It's like, oh, no. I have tracked what they want to see and it makes them mad. And the algorithm's like, oh, all right then. And then they just start shoveling you at content that pisses you off. And you're like, oh, argh. And the algorithm is like, oh, see, I told you, look how much they're watching. Then the other part of the algorithm is like, oh, they're kind of like hurting each other. It's like, oh, they're watching. We were told to make them watch. They are watching. Our job is done. You know what I mean? There's probably a ton of content that if if somehow we could like stream it into everybody's eyeballs, where you learn how to cope with your emotions, if we could like subtly, subconsciously, just like make you cope with your emotions, then maybe that would stop working. Let's think about that. But what I was doing right there was stopping the math parts, because we have to stop the math parts. I used to think commercials were really annoying, but then I taught math class. I thought it can't be all math all the time with no commercials and no breaks. We have to stop. Otherwise, people get angry, but not in the effective, watch the algorithm angry. Because they don't want to come back to class, which is like the default state anyway. You know what I mean? So this is the new part. Look how much the new part looks like the old part. Instead of taking one input and producing one output, now I've got two inputs and one output. Because there are more things that are related. More things that are related. The other reason that this isn't new at all is we're totally familiar with functions of more than one variable. Your grade in most classes is not going to be based on one thing. Sometimes that's summarized as number of points, but we're not making a function of points. Points is a function of other stuff. You've got homework points, and you've got quiz points, and you've got test points, and you've got attendance points, and you've got, like, I don't know, happiness points. I don't know what they're being graded on. But you've got all those inputs that are producing one output, points or percentage. And then from there, we make another function, to this composition of functions. Each percentage corresponds to one grade. So we're familiar with the concept of more inputs producing one output. Some of you know that, for example, if you purchase something with borrowed money, like a house or a car, let's just say house. Let's just all participate in the American dream, and we bought a house in the Bay Area. I mean, fuck it. If we're going to dream, let's go big. So we're buying a house. It's in Hillsborough because we like nice, quiet streets. It's not, there's a function that goes into how much you have to pay every month. How much does the house cost? That's one variable. What kind of interest rate you get? That's another variable. How long you going to take to pay off this house? That's a third variable. There's multiple variables that go in to produce the one output. How much you're going to be paying every month. So we're familiar with this concept. We're going to try to visualize it now, but we're going to try to keep it simple. Once again, we're using the simplest framing, function. One of these variables can be written as a function of the other two. How's everybody okay? I don't know if I opened the homework yesterday, but let's take a brief tour of your first homework assignment. I made this due today, but then we had issues. And it's like, that's probably what caused the issues. I'm like, oh, I'm going to make the first assignment have a due date of tomorrow. Let's really start off strong. So, and then Wiley Plus is like, oh, no, I'm not going to give anybody access to until tomorrow. I'm like, oh, why? And Wiley Plus is like, oh, well, for technical reasons. And then I'm like, oh, Wiley Plus, did you just flip me off? And Wiley Plus is like, oh, no, I don't know what you're talking about. You just did it again. You just flipped me off again. It's like, oh, no. Maybe you should stop referring to me as Wiley Minus. Okay. So this is the one that I was looking for. Here we have a graph, a surface graph of temperatures in the United States. This is an old picture. As you can see, it only goes up to 100 in the Southwest. So just for 2023, just add like 20 degrees all the way across the board. It's like add 20 to the whole thing. And sit there, we can go, oh my gosh, it's so hot. And then we get in our cars and drive home. Everybody gets a V12. So because we're printing this on a flat screen or a piece of paper, we used to have pieces of paper for our books back in the day. But because we're printing this on a flat screen, we can't have it come out, the image come out of the screen at us, right? Because we don't live in Minority Report. We have like Tom Cruise like moving stuff around these things. We don't have like the Tony Stark's lab in his basement. So what we do is we draw lines where everything is the same. So we have to look at this map, and we can see this low part right here in the, because this is in the 60s around Boise. Are the people that wrote this book from Boise? I don't know why they picked Boise, Topeka, and Buffalo. I'm thinking about that too much. We can see that down here, here's where it's in the 60s. So we can imagine that if we're thinking of a surface, if we're imagining a surface, that's going to be a low part. And then we can see it's higher up here. Up here through Nevada, we get in the 70s, and then it's higher in here when we get to southern Nevada, and then down here when we get into Arizona, it's in the 90s. I think Arizona has a law where it has to be in the 90s. My brother-in-law lives in Arizona. It's stupidly hot there all the time. So down here in the 90s, and then down here along the southern border, it's in the hundreds. So although we can't physically represent the height because we have our flat paper or flat screen, we can picture this height increasing from where it's nice and reasonable around Boise, and where it increases, we can see this go up. And we can see how it is bent by looking at these contour lines. So if you look at a topographical map, those are contour lines or level curves. So here's how we imagine a three-dimensional surface, or sorry, a two-dimensional surface in three-dimensional space when we've only got two dimensions to represent stuff with. Not even new, right? We see this a lot. Like if we watch the news, if I had more colors to work with, it would be like all red down here, and then like orange, and then yellow, and then green, and then a little different green. We use the color to represent the height. But we can take those colors, we can take that gradient of color, and we can imagine the lower end parts and the higher parts. The same thing happens on this map over on the wall with people at home can't see. So I guess that's the price you pay for zooming in. I'm just kidding. I'm just pointing to a map that's kind of like a photograph of California. But that's a flat map, but we can imagine where the height is. We can imagine the surface above it. We can see the XY plane, and we just use our imagination to imagine the Z coming out of the paper. Z coming out of the paper with the different colors. Any questions? All right, so your job is to get started on section 12.01, functions of two variables. You can click on your textbook and you can read the textbook. I could assign homework that says read the textbook, and since it's a math class, math students be like, oh, good, no homework. So you could pretend to have read the textbook. And then there's a quiz where things are very simplified down. In the quiz, I want to start looking at different kinds of patterns, because there are a lot of patterns that we're familiar with that I want to make sure that we can quantify. Linear, exponential, quadratic is the first three that we need to worry about. But here, once again, we have this representation where we could see the XY plane, X going across the top and then Y going down the side. We can imagine the XY plane, and here are all the heights above the XY plane. If we imagine that 0, 0 is over here in the corner of the room, and the x-axis is coming out, and the y-axis is going this way, we can imagine that z value of 14, maybe that's up at the ceiling, and then not at the ceiling because I'd run out of space. And people upstairs get really mad when I start pushing functions up into their space, even though it's only like in my mind. So like halfway up, that's like 14. And we can see as x moves away, as we move away from the wall I'm standing by, we can see those z values increase. But then as we move away in the y direction, we can see the y values are decreasing. So we're going to imagine a surface that in this direction is tilted down, but in the x direction is bent up. I just said that in the y direction, it's tilted down, and in the x direction, it's bent up. Is that accurate based on these numbers? It said y is tilted down, implying that's kind of flat, but x is bent up, implying that it's curved. So think about why I said, why I'm implying that it's flat in the y direction, but curvy in the x direction. Any questions? So you've got the first section of homework you get started on, the first quiz you can get started on. The homework has a due date of today. I know that you can't make that day because that's like today. But that's just where we want to get started. The next one is graphs and services, which is what we just started talking about. And even though it doesn't have a due date, you can open up the assignment and start doing problems. Any questions? Comments? Deep thoughts? I told you Cal 3 was the easy one. All right, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.